No introduction.
No introduction.
Okay, so
Daniel needs no introduction.
Right. Okay, so then, do I need an introduction? Let's give the thank you. No, so thank you for giving me this opportunity to present some of the recent results we obtained in the lab just around the corner. The title of my talk is Dynamics of Lasers with Delayed Optical Feedback, Novel Techniques and New Dynamical Regimes. So basically we'll be presenting a few experimental techniques applied to this kind of system which have never been used before, at least in this way. And also how they help us to identify new dynamics and to interpret them maybe at some point. This work was done with basically Miguel, Xavi, Claudio and Ingo. So the system I'm going to talk about is this classical example we use in our group of a semiconductor laser subjected to delayed optical feedback. So here is a fiber coupled version of the setup where we have a laser here an optical circulator which basically just has one input or has 3 ports, and you have a very directive connectivity between these ports, and therefore we basically get the light around the fiber loop in this direction, and the length of the fiber determines the delay of the optical feedback. Here are some other fiber optic components. One is a 50-50 splitter which we use to diverge a part of the light for optical detection. Another part is an attenuator with which we can control the feedback strength, and another is a polarization controller, so we can align the polarization in parallel or orthogonal to the laser light's emission. The typical scenario of such a setup is usually between 1 and 100 nanoseconds feedback, whereas the short feedback delay usually is achieved with free-space optics. We are typically in the order between 70 and 100 nanoseconds in our lab. The feedback strength usually amounts to a few percent, and the polarization typically is aligned parallel to the emission of the laser, at least in all the data I presented in my talk. Okay, so here is a small, slightly different representation just to make this a bit more obvious. So here's a laser diode coupled, or a free-space laser diode coupled, or coupled delayed optical feedback here realized by a mirror and the collimation lens. One of the most direct consequences of delayed feedback you can see on the left here, where typically such a laser diode has a very stable properties, so it has a very narrow spectrum, so basically emits at one frequency, and has a continuous output power which doesn't vary a lot. As soon as you add a bit of delayed optical feedback, the output intensity suddenly changes into these fluctuations, and here the time scale on the bottom on the x-axis is nanoseconds, so you really get dynamics on tens of picosecond range or even faster. So this is one of the first dramatic impacts such a delayed optical feedback induces in this laser. The other one is if you look at the optical spectrum. Here in red you see the laser emission or the spectra without delayed optical feedback, and that's only for a few percent of feedback coupled back into the laser, basically changes into this black curve, which has really a dramatic change, and the spectrum, the spectra broadens significantly and also changes in shape. One way to describe such a system, typically in theory and numerics, is using the Lang-Kobayashi equations, where you basically have the complex electric field, and here you have the impact of gain and the line width enhancement factor. On this term here you have the optical feedback with the delay tau, and on here you have the equation for the carrier dynamics. So one thing here is obviously the electrical field is a complex variable, so amplitude and a phase. And the third term here, important or interesting for me now in this presentation, is the carrier inversion, so electron hole pairs. Just down here is a short summary of these variables. And yeah, so when describing the system or the delayed feedback coupled laser with these equations, a typical way to display the impact of the delayed optical feedback is a representation in this kind of diagram, which is typically referred to the mode ellipse. So here at the x-axis you basically have frequency. In this way here it's basically the frequency of the modes due to the external optical cavity. The black center here in the middle is the solitary laser mode, so you can typically a laser has one longitudinal mode, or emits in one longitudinal mode, and the next longitudinal modes would be split or would be set off in frequency by a large amount. If you now add a long external cavity, you get suddenly a whole bunch of nodes which are much smaller in distance and frequency because the cavity is so long. And this is the effect we see here. So the blue circles here basically describe the positions of the modes, where the red position basically are the antimodes, and this is at the same frequency. It's just different interference conditions, constructive or destructive. And if you now do numerical simulations about the dynamics of the system, you typically get something similar to what we see down here. So here, each one of these vertical lines, you can say, is the dynamics around one of these modes here. So the system enters, or the laser enters this representation from the right, goes down the cavity modes towards the region of higher gain, which is down here. And then as soon as it reaches here, it becomes very close to one of these antimodes. And as soon as it collides with one of these antimodes, it's quickly, basically, re-injected into a region close to the solitary laser mode, or to the low gain region. So here you see, for the representation of these dynamics, just to get an intuitive feeling already, the dynamics are displayed in space of frequency and carrier inversion. So this already shows you that only the amplitude of the electric field is basically not used in one of these diagrams. Just a short note is this effect in the circle is also referred to as the Sisyphus effect. So one example is, or one example for me to see how important it is to get the whole dynamical bandwidth of the system is here the intensity dynamics, which have been studied of these lasers since, I would say, well, decades. So on the top here you see the output of such a laser measured with a rather low temporal resolution system. And you see these things which are referred to as low frequency fluctuations, where you always get a drop in power and then it builds up slowly, and then you get a drop in power. And basically all these drops is always when the laser collides with the anti-mode and then gets re-injected close to the solitary laser mode. The time scale here is hundreds of nanoseconds. And what suddenly happens if you really measure with a far bigger temporal resolution is you go here, and then this whole window is less than 10 nanoseconds, and you see that suddenly there are all these pulsations. So this radically changes the shape of this intensity signal, because, well, if you go past this, then you get this, but it's really important to get the full picture, because otherwise you just miss an important effect of the system. So the overall envelope here is somewhere of megahertz, tens of megahertz temporal time scales. But inside of this low envelope, there's already pulsations which are on the picosecond time scale. And they're due to a partial mode locking between all of these different modes which you find on the mode ellipse, because carrier dynamics, they don't have this kind of time scales. They cannot react on picosecond time scales. They're typically more the order of nanoseconds than these lasers. And basically, if you measure this system with insufficient temporal resolution, then suddenly you get a completely different picture, and the dynamics are actually, the dynamics you measure are actually not really what is going on, is only a part of what is going on. And basically, to go back from this step to really show how important it is to get the full dynamical bandwidth, now I basically want to make the connection how important it is to get also the other dimensions we have in such a system. So here again, the frequency and the carrier density. because to make a comparison with a model which is three-dimensional but you only measure one dimension is tricky. And also, if you want to really tailor the properties of such a system, I mean, you need to understand it properly, and only then you can really tailor it for a certain application. So now, what I'm going to present today is basically how we manage to measure the optical phase and the excess carrier all in real time and in synchrony with the field amplitude, and basically with the high temporal resolution. All measurements present until today are almost all in the field amplitude, so this is really completing the picture. The intensity. Yeah. Okay, so basically now the next section is about the real-time spectral dynamics, which are basically dynamics along the x-axis in this presentation here. Okay, just a very simple high school example is something which you call beat frequency. If you have two sound waves and you overlap them, then you basically get a slow varying envelope, and you get fast oscillations inside of this envelope. And by basically knowing one of the frequency, one of the two frequencies which are involved in this transformation, or in these two sign terms, you can determine the other either by the slow envelope or also by the fast oscillations inside of this envelope. So this is the effect we have been using to get access to the frequency dynamics of the laser, because the optical frequencies are at hundreds or thousands of terahertz. I'm actually not sure how much in terahertz, but it's far away from every technology there is to really measure them directly and with an oscilloscope. So basically what we do now is, before this is the setup I showed you before. Here we have again the circulator, here a power splitter, and then here the polarizer, just to set the conditions. And now here we have a second splitter. And what we do now here is we add a second laser which has no optical feedback, which is ensured here by an isolator and which has a narrow line width. And then on the second photodiode, which is also a fast photodiode with 20 gigahertz bandwidth, we basically measure the interference signal between both of these lasers. And then we can use something like the beating effect I showed you before to suddenly gain access to the frequency dynamics of this of the delayed feedback coupled laser. Okay, so these are the terms we measure. So basically here we measure the optical intensity, but here now we measure the heterodyne term between the two lasers, and then the optical intensity is basically the summation of both fields squared. And for that you get the two squared field amplitudes and this interference term here in the middle, and this is the one which we will be using. So here there is no extractable information about frequency in these two terms. This one, however, will provide the beat signal of the heterodyne measurement. And then just doing some really more or less, doing some very simple maths, you can just substitute the complex fields here by, or the electrical fields of both lasers just by two cosine functions, laser 1 or laser 2. And using, now we say the beat signal is only this interference part here. You can transform this into this equation. One thing I neglected here is basically there's an additional term which is the summation of the optical frequencies, but since the optical frequencies alone are already much too fast to measure in the experiment, we can neglect this term because it's just impossible to measure this. And here we substituted the df of laser 1. We basically substitute just here by the difference in frequency of both of them. So now what is important to remember, this one is the laser which is narrow line width, so basically it's almost like a perfect sine wave, at least on the on the dynamic scale of the delayed feedback laser. And this here is now the frequency of the delayed feedback coupled laser. And now basically by measuring the f, we can set this constant and get direct access to the frequency dynamics, which is what we wanted from the beginning. What is important then is there's some additional terms here which basically make it a bit harder. So here is the term which just comes from the intensity dynamics. So you somehow have to get rid of that, and the same term is basically the multiplication of the two electrical field amplitudes in front of the cosine term also we have to get rid of. So how we do this is basically we do a Fourier transformation combined with some subtraction and deconvolution. Down here you can see basically here S of laser 1 is just the dynamics of the frequency dynamics of the delayed feedback coupled laser. So for that we just take the beat signal, we subtract these two intensities half, and if you remember, this one is what we record here. So basically by detecting intensity dynamics we can make sure that we can clean the signal from any other artifacts, and since this laser intensity is constant, it basically can be neglected because of some experimental conditions of AC coupling. And then to get rid of these two terms here, we just need to make a deconvolution in Fourier space. And then we just have the impact of the spectral dynamics of the laser. So with a, well, let's say rather simple experimental setup, just a narrow line with reference laser, and very simple math, we can actually straight away extract the signal we were after. So to have a certain, or to have a proof of concept, what we do here now is we don't resolve the frequency dynamics, but we just use a time average spectrum of the system. Because for that we have the technology in the lab which allows us to resolve it, and this we trust and has been demonstrated before. And now so you see here in the gray line is basically the optical spectrum measured by a high resolution optical spectrum analyzer. And then here we change the math here slightly, because the optical spectrum of course also includes the intensity dynamics, not only the frequency dynamics. So the deconvolution here is just against the optical field of the reference laser, which in the end we can again neglect. And then, I mean, to an amazing degree, basically these curves perfectly overlap, really on the entire time scale. Until here, we come into a region close to 16 gigahertz, and that's just the dynamical bandwidth of our detection and acquisition system. And then the signals start to diverge. But in this area, both information measured with two completely different methods perfectly agree.
Sorry, could you tell something about the time scales? So for doing this, you need a very narrow and a very precise reference laser. So what is the line width of this laser? So what is the coherence times? Just to compare with the time scales which are in this plot.
So the well, here's no time scales yet. The reference laser has a line width of a few hundred kilohertz typically. That depends also on the time scale. They say 1 megahertz for 10 seconds, 200 kilohertz for a few milliseconds. But basically, the line width of the laser is an additional convolution on top of the signal. And since we measure a frequency range here of 20 gigahertz, the 1 megahertz even will not come into account of this one. Where it comes into account is basically here now. So this gray area is not noise, but actually it's each individual external cavity mode which we can resolve now. And basically this just goes up and down, up and down, up and down for hundreds of times, showing all the external cavity modes. And here, because this is much narrower, here you would have to do deconvolution. But here we integrate for a few hundred microseconds to get this entire plot only, and for that we can assume that the line width of the reference laser is a few hundred kilohertz, and compared to the 3 megahertz line width of the external optical cavity modes, again, it doesn't really come into play. Okay, so basically now we've shown that the method, at least for producing an optical spectra, time average perfectly reproduces what is already used. One interesting fact is by just adjusting the length of the time trace we record, we can choose the resolution for our setup. And now for a perfect reference source, actually this resolution we can push down to 625 Hertz only, which is really very competitive. So the BOSA here, the high resolution optical spectrum analyzer, has a resolution of 10 megahertz. However, the limitation is that all we can measure is inside a range of 16 gigahertz, because otherwise we cannot detect the information we need. And we can clearly resolve the external cavity modes even for such long delay lines as we have in our setup, around 100 nanoseconds. So now going back to what we originally intended here, we do extract now the frequency dynamics. Here's an example plot of one of these low frequency fluctuations I was talking about before. The gray line is the low pass filtered signal, comparing it to the information we showed before, and the black line is again including all the relevant dynamics. And now going to the frequency domain, now suddenly here basically we see the spectral information I was talking about before. So if you look here at 0, we are close to the solitary laser mode, so the solitary laser mode is around 3.2, and the high gain region of the delay feedback coupled laser is between, let's say, 12 and 14 gigahertz. And now comparing this to this plot, basically now we see how the laser goes along the mode ellipse and changes its not spectral properties but the spectral position. So here is one of these dropouts where the laser gets re-injected into the solitary laser mode. From there it starts a drift going to towards the highest gain region, where this drift is getting much slower. But also what is important is here this is information which is different to the typical scalar value which is plotted using this delay phase, because this is the entire spectrum, and it's important to emphasize that at this point there's not a single frequency in the system, it's a spectral distribution. And this can be seen here, and the spectral distribution here, it varies along the position on the mode ellipse, but it's always a few gigahertz. So already from this point, we can extract much more information than is typically displayed. So we record both of them at the same time. One important thing is we do this in the sliding Fourier transformation. So we take a window of a certain size, do the Fourier transformation, get the spectrum, the deconvolutions, and then we slide the window to the next point, and so on and so on. And the window size we chose here was 4 nanosecond, and of course spectral resolution, temporal resolution in this approach go inverse, so you have to find some kind of balance. But for these 4 nanoseconds we get 125 megahertz spectral resolution, which is around 10 external cavity modes. The emission, however, is a few gigahertz in wide, so basically I think this is quite a good approximation. Okay, so here a more complete picture. Again, here is the intensity dynamics of the laser. Right is basically the plot I showed you before. Here the system gets injected at this white areas here, is a re-injection towards the solitary laser mode, and then it moves slowly towards the highest gain region. And this is the information which is somehow comparable to this delay phase information which is so often plotted. And what we used here is we just basically picked the mode with the highest spectral intensity, but it was not a signal averaged over an entire delay time. So as you can see from this signal going from here, you get a much more complete picture about the entire system. Another thing we've been doing with this approach is basically, okay, so now using this data, we can extract a speed, how quickly the laser is on certain positions, or how quickly the laser moves along certain positions of the mode ellipse. At the same time, we can fit each individual of these external cavity modes and extract a line width. And then by fitting the width at each time step of the entire optical spectrum, we can basically calculate the time scales the system is in each one of the modes. And on the top here, you see the line width plotted in hertz of each one of these external cavity modes. Here is the solitary laser mode, again the highest gain region, and you see a slight decrease in line width around the highest gain region, which is what you expect. But the surprise is here. Basically, if you calculate this time and this area, both data agrees perfectly almost. But suddenly in the highest gain region, you can always see already see it from this plot. The relaxation rate drops dramatically. I mean, almost by one order of magnitude. And this is not reflected in the line width of the external cavity modes. So this is why we attribute this more or less constant line width of all these modes to dephasing effects rather than relaxation effects. So this again is some information which is new and extracted using this technique. Now let me go to the next variable of the system, the carrier inversion, which again here is used to display or to illustrate the mode ellipse. So how do we do this? Here you see a closer picture of actually the laser we are using. So here this tiny dot is the laser itself. From there goes the tiny wire bonding to a small platform here, and then via a connection we directly connect it to the high frequency cable, to the high frequency setup. And here's the schematic illustration. So here's the laser, there's this thing which we call an impedance matching resistor, and then there's something called a bias T. And a bias T is basically just diverging DC and AC signals. So DC is going one direction, AC is going another direction. And now what we can do is we can bias the laser with a constant current, and then we can modulate. And for this we need the impedance matching resistor. However, we also can turn this around. We can bias the laser with a certain current, and then use this as a readout rather than an injection source, or a way of modulating the laser current. And for the free space, in this case it's necessary because otherwise we can never reach high frequencies, because if you have a big housing attached to this, just the capacitance of the housing and of the entire setup will really complicate things a lot, and you can typically not reach frequencies higher than 2 or 3 gigahertz. And we've seen the dynamics reach 16 almost. So it's really important to go to a different way of doing this experiment. So, and to inject the signal, we use the impedance matching resistor. To extract it, we discard it. So here's a short characterization of the setup. So what we've done is we apply a constant bias current, and then we inject a modulation current, which we select to be much smaller to get the small signal response. And then we record certain the response curve of the laser. And by increasing the bias current, you can see that the current, that the frequency of this, the dynamical bandwidth of the laser increases significantly. And this is basically textbook responses here of displaying the relaxation oscillation frequency here, and above the relaxation oscillation frequency, the response of the system almost just dies away. So this is basically confirmation for us. We can at least go until 8 gigahertz or extract signals with 8 gigahertz bandwidth without seeing any artifacts which are not due to the dynamics the device is actually performing. Okay. The other way, if we connect setup, is just this way. We have the bias T here, so the DC signal is going this way, the AC signal is being injected or is being extracted at this point, and then we just connect it directly to the oscilloscope here. Due to the bias T, we have a low frequency cutoff of 10 megahertz as well. So we should have a dynamic range of 100 megahertz to 10 gigahertz. So we should be able to capture the entire dynamic range of the carriers. And just a technical terms or aspect is if you determine all 3 variables of the system now, synchronization suddenly becomes important, because signals at this speed, as soon as you have more than a centimeter of difference in propagation path, suddenly they are delayed. So you need to find a way to synchronize them. And basically by carrier injection, we can then synchronize each one of the signals, which then, it's only a technical term, but it becomes quite tricky at some point. Okay, and now to go directly to the additional data we extracted. On top again, we see the intensity dynamics of the laser. One step below, we see this the spectral dynamics, again only represented by the scalar value to make the comparison a bit more easy. And then at the bottom now, we directly see the dynamics of or the voltage drop across the laser. This is not now exactly the carrier inversion, but it's the voltage drop across the laser which we measured. So we will be working on this, but this we still need to convert into the other variable. But you can already see that all of these events are nicely synchronized. So here you see the power dropout, You see here the drop in the in bias, and here you see the corresponding response in frequency. So now, in all 3 dimensions, we can nicely characterize the dynamics the system is actually undertaking due to the delayed optical feedback. To go in a bit of slightly different representation, which is also always many times used by modeling, is now we make an equivalent to the phase space. Here, instead of plotting against time as I did before, I just plotted against the 3 other dimensions we extracted. So here is the frequency. Solitary laser mode is around here. Then the laser basically goes down here along the modes of the external cavity, and as soon as it reaches the highest gain region, at some point it collides with the anti-mode and it gets rapidly reinjected into the region of the solitary laser mode. So this is rather textbook, it's almost like you see it in many numerical simulation. And this is also important because now we can actually do a direct comparison with the model, and this was important because, for example, a few years ago there were still discussions what is really the effect behind this behind these dynamics. Is it interference in external cavity modes? Is it with other longitudinal modes? So basically now we can really pinpoint the effect that these dynamics really are happening on this modulus picture. And as I said before, determining parameters and tailoring the dynamics per applications, all this is basically required or useful. However, after having access to these additional 2 dimensions, we now suddenly got pretty surprised. What we noticed before is we can either have these kind of nice and smooth LFFs, so there's a dropout and then it builds up again and then there's a dropout. So basically, like you would expect. We were also sometimes observing a structure like this, which at many times still has an envelope, which is similar to the low frequency fluctuations. But inside of this, there's always these kind of windows which are spaced by 1 delay time. And we were always wondering, what is this actually? And now by looking at frequency dynamics, you can really pinpoint what's going on. So instead of the laser now going basically going from the high gain region being ejected back to the sort of laser mode rapidly and then making a slow excursion along the external cavity modes, you can see that the system is basically almost like oscillating between the 2 areas of the modal ellipse, so the high gain region and the low gain region, which before was, as far as I'm concerned or as far as I'm aware, was never observed and also not described. And the same effect we can see down here. So here suddenly, instead of having these regular drops and then just this build up, suddenly we get a whole bunch of drops, and also different is they become positive in voltage, which was also not really observed before. And here you can see that this is not just a very broad spectral emission where the mode which is the most active is switching between the 2 regions, but it's really the entire spectrum shifting between the high gain region here and the low gain region here, which you can see by these white lines. So basically the spectrum remains the same width, but suddenly it goes from here completely down here. Remains here for a bit, goes down here a bit, and only a time average envelope is basically displaying similar dynamics as in the classical low frequency fluctuations. This difference becomes even more dramatic if you compare it in the 3-dimensional phase space representation. And important at this point to mention is that the experimental conditions or the parameters which we drove the laser with are exactly identical between these 2 graphs. So it's the same time trace. There's some sections where you see the slow, nice low frequency fluctuations, and there's some areas where you suddenly see a dramatic change in behavior, and suddenly it becomes there come these tau packages. And the effect here is basically again the normal LFFs going down to the highest gain region, and then you see this reinjection. Here you don't see such a structure. You see the system always tends a bit going down here, but then it goes more or less in a circle. It goes up, down in voltage to the solitary laser mode, which would be the normal direction, but then it also goes this way, and this is completely not present in this presentation. This effect comes a bit more visible if we look in 2-dimensional plots now. So here, for this typical smooth LFF dynamics we have seen before, on the top graph you see the drop across the laser bias junction. Again, here you see frequency, so here solitary laser mode, high gain region, the system gets rejected and then goes this slow excursion around here again until it gets reinjected. And here you see the power, basically, the equivalent plots, but now intensity versus frequency, and you see the build up in power until it hits the anti-modes close to the high gain region and then it gets reinjected. If you now look here, the biggest difference is really in the bias drop which we observe here. And what we think we see here is basically a direct channel which was not observed before, because before there was basically a connection from the high gain region to the solitary laser mode, just using this dropout going to clockwise and going to a lower bias drop, so basically higher carrier inversion. But now suddenly there's this additional channel connecting the low gain region, so the solitary laser mode, directly to the high gain region, which are passing through all the optical modes on the external cavity. So basically, this is we think this is an additional channel for excursion on the mode ellipse without using a large part of the optical modes. And one different representation we can use for this data, this is all the same data, is basically we do a comparison to some kind of a spatio-temporal model. So instead of displaying the data in 2 or 3 dimensions, which are the physical variables of the laser, we basically take the time traces again, but now we convert them into matrix, basically here on the x-axis showing the one delay time tau, and then just stacking them one delay time after the other. And then we can see again in this representation what happens for the dropout, which we've seen before in the LFFs. So basically all of these white lines is the time when the laser was actually re-injected into the solitary laser mode or to the low gain region, where the black lines is when the laser, or the black areas is where the laser is very close to the high gain region. You can also see similar effects when you look at the same temporary, the same spatio-temporal like representation of the intensity dynamics, and so also for the bias drop. But for the frequency dynamics, this becomes really vivid. So the coupling here is basically in positive x direction due to causality, and in positive y direction due to the optical feedback. After 1 tau, the laser receives the optical feedback, and basically this is the coupling if you would compare this to a spatio-temporal system. And now, comparing these two situations, again, here we have more or less regular LFFs, the ones we observed before, with the optical feedback attenuation of 12 dB. On the other side here, we just increase the feedback by 1.1 dB, so it's really a very small amount, and suddenly this really starts to...
you increase the feedback or you
the feedback attenuation, so we lower the feedback, sorry. Exactly, and then suddenly these very more or less straight lines, which correspond to a dropout in 1 delay time, or to one of these re-injection of the entire system in 1 delay time, again to a spectral position close to the solitary laser mode. Suddenly we don't see this anymore. A part of the system is re-injected from the high gain region to the solitary laser mode, but then already it goes directly back where it was, more or less. And then suddenly these fronts are forming, which are also in directivity in the reverse direction from what you would expect from this coupling topology of this representation. So it really becomes a very dramatic change, and we think that basically these fronts are more or less a different representation of the same effect, but they make it nicely vivid. You can see basically what happens in 1 delay time. Instead of the entire system being put back into a different area in phase space, only part is re-injected while it stays there, or it just goes back directly again. Okay, so to summarize, I've represented the first real-time measurements of all the 3 physical variables of such a delayed feedback coupled semiconductor laser. The technique, however, is not limited to such a system. It's basically just the simultaneous detection of intensity, frequency, and current dynamics with up to 16 GHz temporal resolution with the frequency of course you have to make the trade-off between temporal and spectral resolution. This could be used also to have a closer look at injection locking, to optoelectronic feedback, to current modulation. So it's really a very flexible tool, and it's with a very broad applicability. And already the first measurements, I mean, directly from using these techniques, directly we find new dynamical phenomena which so far have not been reported before. So this again underlines a bit how important it is to really look at all the data which is describing such a system. And then using a spatio-temporal representation of the data we extracted, maybe one gets a better feeling for the dynamics which are going on, and it also underlines a bit the similarity between the delayed feedback system and spatio-temporal dynamics. And on a different point, so this is something I've been doing in the lab the last few weeks. So what I'm trying to establish here is going a bit away from only a single delayed optical feedback coupled laser, but actually to build up a network of lasers. So what you see here on the top is an array of 63 laser diodes. This is a rather weird number because it's an 8x8 array, but the company couldn't connect one of them because they ordered the wrong socket. And basically at the bottom here you see the optical setup I'm building up right now. This here is a spatial light modulator. So basically the optical emission propagates this direction. There's some optical elements like lenses and a diffractive optical element. And basically what the diffractive optical elements does is, it's hard to see right now, but it basically couples all direct neighbors of one laser to this laser. So it is we can introduce a coupling topology between self-feedback, the delayed self-feedback of the laser, and coupling to all the neighboring lasers. Using a different diffractive optical element, you can also adapt what kind of coupling topology you want, and using the spatial light modulator we can then adjust the strength of the coupling. And here you see the front of the laser setup here, so in the middle here you see basically this laser chip, and then just the socket and around everything, and here you see the connections. And I just wanted to present this, so I'm going to use this first for other things than really studying the dynamics of such a system. And I'm going to be using it for a different project to do reservoir computing. But however, I mean, it's the Institute of Complex Systems, so if someone has a good idea.
How they are coupled with external feedback, or is you mentioned diffractive coupling?
So basically the feedback
so it is an external feedback to the whole system.
Yes, so basically this here is something like a mirror. So the light comes here, bounces back and couples. However, then you don't have a network, then you only have 63 lasers with self-feedback. So what you can do then, you can play a bit of tricks with Fourier optics. The lens here does a Fourier transformation and gives you a certain angle component relative to the spatial distance between this one. If you now take a diffractive optical element which introduces the same spatial frequency into the system, suddenly you can basically go from a spatial coupling into angle coupling, and then where each of these lasers forms a point on this mirror, suddenly if you put in the diffractive optical element, it will form 9. One of itself and the other one around it. And if you match the parameters of the lenses and of this diffractive optical elements, you can basically couple the neighboring laser. So hopefully. I mean, so far all lays, so I'm really happy for that, but okay, thank you.
So questions? Comments?
Regarding your last experiment, or this one actually, I will present this.
This one?
Yes, this one.
Yeah.
You mentioned the coupling into the feedback delays of the order of 1 to 2 nanoseconds, which is rather short.
Yeah.
Is the line shape of these VCSELs that you use especially narrow compared to the edge emitters that we usually use, or what do you think?
The line width. Yeah. So that I cannot measure at the moment because well, the high resolution spectrum analyzer doesn't go to these wavelengths, and the other one doesn't provide the resolution. They shouldn't be too different though. So I would expect something couple of megahertz, 100 megahertz, 10 megahertz. Yeah.
So you assume that still this order of magnitude of the feedback delay won't go below the current cycle?
Well, yes. Yes. So let's see what happens. But since I'm well, for the reservoir computing, I don't need to go basically below this regime or above this regime. These lengths here, they can be adjusted. The defining element of this one, of this length, is basically the diffractive optical element. So by adjusting a diffractive optical element or just putting here a spatial light modulator, a phase modulator, you can basically realize practically what lengths you want. But for this setup, I chose a certain element to make it also compact, and with that, this length is given. This length cannot be changed by, but this can for sure be adapted to 10, 20 nanoseconds.
It will definitely be coherent coupling.
Yeah.
Any more questions?
This strange regime of low frequency fluctuations in which you have the right one, is this related in any way to this other regime which is called coherence collapse, which appears higher in threshold? It's a different, completely different thing.
Yeah, but this is very low in threshold, so I would say it's not already above the coherence collapse. It might be at the boundary. It's hard to say at the moment. The problem is you cannot really measure these kind of dynamics for higher pump currents, because then the spectral width of the system gets bigger than the 60 gigahertz. So this is basically the current limitation we are facing.
But that phenomenon is not related to the coherence collapse.
I wouldn't say
coherence collapse, you would only again consider the upper half connections, but the lower half connections, no.
I mean, you can see here basically this escape, this channel here doesn't exist, the lower voltage channel, and it also doesn't exist in models. It basically goes here and it goes to the anti-modes, but it stays in this area, and here suddenly we get this completely different. I mean, the external modes should be somewhere here, so here it drops really significantly below this. So, and in terms of regime, I would say it's rather far away from the coherence collapse, because you can't even measure this for the spectral resolution at the moment.
Don't they come from the same time series? Different pieces of the same?
These two, yes.
So even not a changing parameter?
No, same. No, it's the same parameters. This is basically at one position, one temporal position. This is one time trace. This is one really long time trace where you see at one section you see really nice LFFs, and suddenly the dynamics change, and it goes from here to here.
It is as it is. Once you have such a jump like in the lower half, it propagates.
Yeah.
David?
I have a question about one of the first transparencies. The one which you show intensity as a function of time and this low dynamics and fast oscillations. But you mentioned also these later.
One of these?
Yeah. Next one.
Next one.
Yeah, this
Yeah.
one. So there is a very similar effect in semiconductors, which you apply a DC bias, everything is steady here. And then the current response is also oscillates as a function of time. Now, if you do this in, let's say, bulk, then you don't observe these fast oscillations. You just observe these slow dynamics. This is the kind of effect which may be familiar to some people in the audience, which I studied like 30 years ago. But now if you construct an artificial lattice, then also the semiconductor, then you also observe these fast oscillations. So the presence or absence of these fast oscillations is related to the discreteness.
But this is again the same conditions. This is basically zoomed into here temporarily. This is no change in system conditions or whatsoever. This is just measured the same system with a low bandwidth detection system, And this is here I just want to illustrate that it's important to really be able to measure the entire dynamics, because there you could basically imagine the system is more or less coherently slowly drifting on a mode ellipse after being reinjected close to the solid laser mode. But no, if you really measure it with the entire dynamical bandwidth, you see that there's all these very strong fast pulsations which are on the same order of magnitude. So this is, as far as I'm concerned, aware of, this is the same conditions.
So you never get rid of these fast oscillations?
No, they are there.
Okay.
I mean, well, yes, they're not for all conditions, they're not always there, but it's not that you get either this or this. This is inside. I mean, one graph maybe to illustrate this is this one. So basically, so the gray line would be what was displayed before as the slow dynamics, but in reality, if you measure the system with the appropriate dynamic bandwidth, the black line is the real signal. This is not different conditions, just different measurement systems.
May I add something?
Sure.
But the stable state always exists in parallel to this dynamical state, so in that sense you're right. So there is a bistability between the dynamical state and a time-independent stable state.
Yeah.
What do you think? Do you think any of those things can be described in the framework of the Lang-Kobayashi equation? For example, the answer for this additional channel probably is you don't know, but I don't remember. I don't remember if the Lang-Kobayashi equation allows a broad spectrum and not a shifting frequency. In usual plots, you see
no,
you only plot a shifting frequency. I don't know if the Lang-Kobayashi.
No, I think the difference here is basically you refer to this data, basically what I call equivalent. So I think this is just a extractor method in the Lang-Kobayashi equations. Basically, what is done is you measure the phase, or you simulate the phase over the entire delay time, and then you just normalize it with tau. If you would just do a Fourier transformation of the same information, you would also get this graph. It's just not being displayed. So physically, it should be the same. It's equivalent.
Just a clarification. Did I get it right? When you observe this new trajectory is below, is when you observe in spatio-temporal picture those walls?
Exactly. So they are, well, I mean, to really exclude one or the other, I cannot be 100% sure, but so far, always when I observe one, you saw the other.
I first understand. In numerical simulation of the Lang-Kobayashi regime, or for the Lang-Kobayashi equations, this new regime is never observed.
Oh, we're not aware of it.
Yeah.
Can you repeat that, please?
That in the numerical simulation of the Lang-Kobayashi equations, this regime is never observed.
This one?
Well, it is observed.
This one you've seen?
This one is observed.
I mean,
That we go, that basically the other channel is the same amplitude and presence almost as the other direction.
Okay, I have to go back a bit, but in the intensity domain, I've seen that.
No, but intensity domain, look at this. Intensity domain looks very comparable.
Yeah,
There's only more channels.
but these sudden switches.
Okay.
Yes. Yes, but I just have looked at the upper right domain.
Yeah, but I think what Perry referring to is this additional channel here,
No,
going below the modes.
What I wondered is if under some parameters, the Lang-Kobayashi equations numerically show this, or is something that is never observed in the Lang-Kobayashi model, and claims that one requires additional things to model.
Would be nice, but would be interesting.
More questions? Comments? So if not, let's speak again.